we're finally going to get to the last part of this section. And what we're going to do is we're going to go through and we are going to ensure that we can finish solving these types of differentials that involve the unit step function. And you might recall that we had this forced motion system and we had a unit step function and we're going to solve it. This is actually a really cool problem to finish this off because we're going to use some trigonometry to help us with the inverse Laplace and Laplace transform. So we got to this part, all right, and we just have to take Laplaces at this point. So we're going to take L of x double prime plus 16L of x plus 2L of cos 4t. All right, and all of that's pretty easy. But now we get to this guy. So 2 Laplace, and I'm just going to run to the next line, of the unit step function of t minus pi cos of 4t. All right, now here's where it's going to get really sneaky, all right, because we need to take the inverse Laplace, or the Laplace of all of these, and none of them are too difficult except for, of course, the one that contains the unit step function. But let's do all the other ones first, all right? So the first one is just going to be s square L of x. So we get our s square L of x, right? And then we're going to have minus s of x at 0, and then minus x prime at 0, right? So that's just this animal right here. Plus 16 L of x, all right? So that's not so bad. Is equal to twice. Now, this is a 4t, by the way, in English. This is our cosine function with 4 as our value inside, but it really doesn't matter too much because we're just finding the cosine of that. All right, so we have that. Remember, we have our form s over s squared plus k squared, where in this case k is 4. All right, so that's going to be 2 times s over s squared plus 16, and that's from this guy right here. All right, so let's just hold on to all of this. And let's now focus on the tough part. All right, so this guy right here. So I'm going to write it in orange. So we want to find minus 2 Laplace of unit t minus pi cos of 4t. And let me write it like cos of 4t like this. All right, now, one of the things that we have to do, and this is the really tricky part about unit step functions, is we have to have t minus pi right here, all right? Now, one of the tricks that we usually do is we say, okay, well, I can add pi and I can subtract pi, all right? And that would get us to what we need, but then we'd have to use a sum and difference formula, okay? So we don't want to do that. All right, so let's forgo it this time. This is a really special problem, all right, because we can do this, all right? And you might be asking yourself, well, why can I just subtract 4 pi? Well, you might remember if you subtract 4 pi, that just means you're going around twice in a clockwise direction, all right? So in other words, it's a coterminal angle. Remember, you can add 2 pi n, or you could subtract 2 pi n, and you could still maintain a coterminal angle, all right? So this is a trick whenever you're doing trigonometry, is to remember these coterminal angles. Now, I added and subtracted 4 pi because what I can do very nicely is I can factor the 4 out of this cosine right here. And so I can write that as 2 Laplace unit step function t minus pi cos of 4 quantity t minus pi. All right, and that helps us a lot. That's going to help us to get to that unit step function that we need to find the Laplace. All right. Now, when we go to find the Laplace of that, we're just going to use our second translation theorem, where a is going to be equal to pi. Right? And then we just have our cosine of 4t. Now we know that the Laplace of 4t, we can use this rule, s square plus k square. All right, so we're still going to have that a, or k, excuse me, is equal to 4. We have a is equal to pi and k is equal to 4. And we have minus a to the minus as, right? And we have that minus 2 outside. So now let's copy everything down, right? And by the way, you might remember in the original problem that we had an initial downward velocity of 1 foot per second. So x prime at 0 is 1, right? And it begins at equilibrium, so that means x at 0 is equal to 0. Right? So that actually helps out a lot because x at 0 is 0, and this is just 1. Right? So after we copy everything down, right, we're going to wind up with s squared minus 1. I'm sorry, s squared Laplace of x. So s squared Laplace of x, and we're going to get minus 1 plus 16 Laplace of x. It's going to be equal to, we have 2s over s squared plus 16 from right here. And then finally, we just use this formula to find the last part of it. I'm just going to add it to the end. So it's going to be plus e to the minus, or excuse me, minus 2, because we have the minus 2 from right here. Right? So we're going to have minus 2 e to the minus pi s. And then we're just going to have s over s squared plus 16. Right. We're going to add 1 to both sides and factor out the Laplace. Right? So if we do that, we're going to get L of x times s squared plus 16 is going to be equal to 1 plus 2s over s squared plus 16, and then minus, I'll just combine everything together, 2s e to the minus pi s divided by s squared plus 16. And now comes the fun part. Now we have to divide through by s squared plus 16. All right, so that might make it a little bit ugly, but not too terrible. So that's going to be equal to Laplace of x equals 1 over s squared plus 16. We like it. Plus 2s over s squared plus 16 squared. Could be worse. Minus 2s e to the minus pi s squared plus 16 squared. All right, so now this looks really ugly, all right, but there is some good news because now we're just going to take the inverse Laplace of each of these. And the good news is, if you look back at your table, a lot of these are actually really nice and easy. All right, so what we're going to do is we are going to prep these. Okay, so to prepare them, we're going to look back at the table, and we probably noticed that this has the form of k over s squared plus k squared. This one, and actually these two, have the form of 2k divided by s squared plus k squared squared. All right, so, and by the way, 2k over s squared plus k squared is going to be that t and then sine kt. All right, so this is one that we haven't used too often, but it does exist and it's really nice to use. All right, the only thing we have to worry about is right here. We can't forget that, okay, well, we're going to have that second translation here. All right, but for right now, let's just go through and figure it out. All right, so get rid of all this stuff. And we're going to set everything up by multiplying by whatever coefficients are necessary. All right, so we're going to inverse Laplace, and we're going to say that x is going to be equal to Now I'm going to multiply by 4 and 1/4. So 1/4 inverse Laplace of 4 over s squared plus 16. That's a pretty easy one. We need to get an 8 in the numerator. And so to get an 8 in the numerator, we have to multiply by a fourth and 4. So this is going to be 1/4 L to the minus 1. And that's for this guy right here of 8s over s squared plus 16 quantity square. All right, so that one's nice and easy right now. And then the last one, well, we're just going to ignore this e to the minus pi s for right now. And we're actually going to do the exact same thing that we just did in the previous, is we're just going to multiply by 1/4 and 4. So we're going to get minus 1/4 inverse Laplace of 8s over s squared plus 16 quantity square. And then we still have that e to the minus pi s. All right, so let's just go through these one at a time and we'll be done with this. So first one, we'll do this one in black. That one is just literally 1/4 of the sine of kt. All right, so in this case, k is 4. And so it's going to be 1/4 sine of 4t. All right, so that's nice and easy. That one doesn't matter all that much to us. All right. The second one, oops, not sure what happened there. Let's get rid of all that and try again. So x is going to be equal to 1/4 sine of 4t. Nice and easy. The next one, right? Now this one's easy too. This one is just going to be it's going to turn into 1/4 of the t sine of 4t. Right? So this is going to be 1/4 t sine of 4t. Right? And right here, we can see that k is equal to 4. Right? So right here is 2k, and right here is your k squared. So it fits that form. Right? So that's these two. Those are the easy ones. Now the not so easy one is this guy right here, because it's new. We're going to have to use the second translation theorem, which means that we're going to have a unit of t minus pi, but then also the t is going to get replaced by t minus pi as well. Okay, so that one is going to turn into our 1/4 still. Right, so I'm just going to write this below. So minus 1/4, and it's going to be, instead of t, we're going to have t minus pi. Okay, so right here we had a t, so we just turn it into t minus pi. Same thing for the sine. We are going to have sine of 4 quantity t minus pi. And I'm going to do this. So we know that the sign is encumbered by both. And then finally, we have our unit step function. All right, so that's our solution to this one. A little bit nicer than what you would imagine initially, just because we looked at the Laplace, the inverse Laplaces, and we thought they'd be really ugly, but they actually turn into something nice. All right, so hopefully this illustrates how to go through and use the unit step function, what the unit step function is, and then also how to go through and to be able to take Laplaces, inverse Laplaces, and then to solve differentials involving it.